In this nugget, we're going to dare to compare network topologies and see what's required in order to support NSX. So what does it mean that we're going to be working with NSX, creating a logical network using VXLAN? Well, let's envision our ESXi host platforms. The purpose of those platforms is to host virtual machines. The power of the VXLAN is that we can connect all of these devices to what appears to them to be the same logical switch. But the reality of what's going on under the hood could be completely different. And that's because the only real requirements for the physical network are that 1, they support IP connectivity, and number 2, that in order to support the VXLAN header, they support jumbo frames. Now, one way that could work would be with a series of top-of-rack switches that are functioning as simply layer 2 access switches with gateways that support routing both east to west and north to south. In other words, out of the network into the rest of the data center, as well as supporting the connections back into the local network. So with this particular simple network design, what are the pros and cons? Well, one advantage of this particular layout is that spanning tree protocol is not necessary because we have no switching loops to avoid. Another concern at the switch level is, what about that MAC address table? Is it going to be small or large or somewhere in between? And because each switch really only needs to know the MAC addresses of its local broadcast domain, which might look like that, we're going to end up with relatively small MAC address tables with this particular layout. And then there's the concern about scalability. It might work now, can it grow? And the answer for this particular layout is not well. Now, while this infrastructure can support multiple VLANs, the IP addressing must be unique for all entities on one side of a router. A router must be sure that an address is going down one path or another because there is no switching going from these routers. It's pure IP routing. Our scalability limitation then is based upon the number of ports that we have access to in the access switch, and if we want to have unique networks that are isolated from the other networks, a new IP space to work with, that will require yet another port off of the router in order to create that infrastructure as well. So definitely some real issues with scaling. Every time we try and scale, we're going to run into either layer 2 or layer 3 reconstruction limitations. The other question might be, how many VLANs can we create? And the answer is we can support up to 4,094 VLANs for each one of these legs off of the main router. Because they are hidden from each other by having to pass through the physical router before reaching another one, we could have a virtual machine on VLAN 500 off of this ESXi host, and another virtual machine off of this host also using VLAN 500, have the switch be able to forward that. However, the IP space would have to be different. They are not actually the same network because we're in a separate switching domain. Now, one common way to re-engineer this particular network would be to replace the gateways out of the network with multi-layer or layer 3 switches. So now, if that layer 3 switch up at the top needs to forward a frame, it can do so because it's a layer 2 device. But if we have a particular packet addressed to the default gateway that's represented by that layer 3 switch, then it can forward that frame functioning as a router. So this gives us the best of both worlds. But let's break it down again to those questions of scalability. Spanning tree protocol is there to prevent layer 2 looping, which would cause a broadcast storm in the network, among other issues. And we can see that there are many layer 2 loops between switches that are now possible to create. So spanning tree is going to need to jump in and actually block some of these redundant paths, disabling some of these extra links to ensure that all frames can only have one path that is used in order to get to another destination. No redundant paths are available. It's just a fork. We can have forks in the road, but we can't have a loop. So spanning tree protocol is going to be on, and that means that we're not actually able to use all of our links. What about the MAC address tables? Again, because of the layer 2 communication, our MAC address tables may well end up holding essentially all of the devices in the entire network. So this is going to be very large. Our scalability is actually pretty good. We can add more devices and more switches, though there's going to be some concerns about the size of those MAC address tables and the speed in which it can forward traffic and the redundant link issues that are going to actually put a cap on some of our bandwidth capabilities. And when it does come to scalability, we do still have the limitation at the VLAN level, because now we have the ability to support 4,094 VLANs in the entire layer 2 infrastructures. So we started with the star topology. We extended the capabilities of the star topology by adding the multi-layer switch. Can we enable any more scalability? The answer is yes. Let me show you how. The next level of extension is what we call the point of delivery network design. And it's really the exact same design we were just looking at, only we now bring up another device. We bring back in a routing gateway. By adding this high-level routing service before working our way up to the data center itself, we allow the idea of having separate pods, point of delivery. Everything on one side of the routers becomes by nature isolated from anything on the other side of those physical routers. So what could be over there? Another pod. So let's think about this from a scalability perspective. Is STP going to be on? Well, sure, but within that point of delivery network. Will we have large MAC address tables? Yeah, they can get large, but scaled within the pod. If it starts getting to be too much for the switches to handle, we could break it apart into a separate routed network. So when it comes to scalability, our scalability is actually pretty huge. And that's because we can have 4,094 VLANs per point of delivery network. But the point of delivery model is not the only way to increase scalability. Another option would be to actually use what's known as the collapsed access layer. So for this model, we're going to be replacing our layer 3 switches with router. But wait, we worked so hard to actually have that combination of routing and switching to give ourselves flexibility. True. But here's what we're changing now. We're collapsing the access layer to the point of access so that now these devices that our ESXi hosts are directly plugged into are now layer 3 switches. There are no switching loops, therefore there's no need for spanning tree protocol, and all of our links are up. And our MAC address tables are going to stay small once again because we're working in an isolated space. Our VLAN controls are going to be once again limited per rack. Essentially, this is much like what we saw with the pod design, except now the pod has been scaled down to a single rack. So the scalability for this is good because we have no STP and a small MAC address table, but in terms of growth, we're dealing with the number of ports that are available off of the switch ports in that rack. And when we add a new top of rack switch, that's going to have to be a new separate environment. Now there's one final topology that I want to make sure that we're aware of, and that is what is known as the spine and leaf topology. Now when we move to a spine and leaf architecture, we see all of our ESXi hosts are connected to access layer 2 switches. But these switches are specifically referred to as leaf devices. And we'll notice that our default gateway and access to the data center is going to be governed by some layer 3 switches, which are connected to again by some layer 2 access switch, which are again functioning as leaf devices. All the communication that we see below the red dotted line is what we would think of as standard network Ethernet communication. But up at the top here, these devices are not switches. These are what are known as spines. And these spines are connected to our layer 2 access switches. But above the red dotted line, the spines are communicating with the layer 2 access switches using a protocol called TRIL, the transparent interconnection of lots of links. It's an open standard that replaces STP. And the beauty of TRIL is that it has its own built-in loop avoidance, so no links need to be blocked. But now, because the broadcast domain extends across all the racks, we do have larger MAC address tables. When it comes to scalability, we do have very good scalability because we have fully utilized uplinks, and really the main limitations that we're going to run into would be at the MAC address table level and the fact that because this is shared across the network, we are limited to 4,094 VLANs for the entire infrastructure rather than just for any one particular rack or pod. My friend, if you didn't know them before, you've learned a lot of different network topologies now that can support NSX. But the beauty is NSX doesn't care. It's going to be running VXLANs on top of whatever infrastructure you place. It's going to ignore your VLANs as long as you have a functioning transport network that supports IP and that supports the jumbo frames, you're good to go. So that means we can focus our attention in building our physical network and extending our physical network on questions of scalability, not on service. I hope this has been informative for you, and I'd like to thank you for viewing.